Okay, boleh dengar semua? Can you all hear me? Clear?
Yes, sir.
Ahmad Sulaiman. Okay, thank you. Okay, if you take a look at this question, so a few amendment we need to do, which is please delete this part 175 ohm. We shall use instead of 175, we shall change into 275 ohm. So use 275 ohm for this value and 275 ohm. Okay. And also another one is your 2000 ampere turn into 1000 only. Okay. 1000 ampere turn. 1000 ampere turn. So use these two numbers as our current exercise. Okay. Okay, let's take a look at this question. Okay, we have here. You can see, yeah. I hope you can perform the exercise together with me. Okay, we have here. First thing that I have to do when you have a question, please take note and recognize. Is it a motor or a generator? And motor or generator? So we are talking about motor now. So what connection is this? So we have a shunt connection of motor. So what you have to do, please sketch a diagram for that particular motor. So means that if this motor, the diagram should be in shunt connected version, which is like this. Okay, please draw. So this is shunt connected. So shunt connected. And then please key in or state all the data that being issued. And so what data that given here? So we have 30 horsepower. We have 240 volt of the terminal. And we have rated current of 110 ampere. And we have what else? The things that we can key in. So directly we key in into the diagram. So we have here RA given, B terminal, IF, RF. So write all the information and into the diagram or where it gone. Into the diagram or at the side now. Okay. We have here 30 horsepower, 240 volt, 110 ampere. Okay, P rotational. 3550 watt. Okay, the things that we can key in is our, let's say our RA, which is 0.19. Then RS. So RS usually will be in series with our armature. So you can draw here the element of your R, which is here is your RS. 0.02. Then R adjustable RF75. Then your R adjustable 100 to 400. So your filter 2700 turns per pole. So your terminal voltage 240 here. So what else? See? So since this is your motor, so you can sketch the arrow of your current. So motor means that we are providing the terminal voltage and the current will flow into your system and it goes here, will produce your rotation of your shaft. See? So your P in is electrical, P out is your mechanical, and this is your P out. This is your P in. So you can draw, sketch your input flow, which is this is your IL, I load. This is your IA, and this is your IF. Okay, IL, I am amateur, load, armature, and field. And okay. Draw, key in, P in, then you can state your or derive your equation from here. And so what equation you can see regarding the I? So IL is equal to IA plus IF. And other than that, since this is your motor, so VT that comes in will be flow throughout your I RA plus RS and plus EA. This is your equation for this part. And other than that, you can see IF is equal to BF divided by RF total. See, what is equation here? This is the general equation you can get or you can derive from this itself. Later, because the input is electrical, output is mechanical, so we need to find what is our EA output. So you can rewrite also EA in terms of EA equation is equal to VT minus I RA plus RS. Okay. Same, you just arrange such that the EA is placed in front. Okay, this is the equation for your reference. Okay, if you scan through the question, you need to find the efficiency, so you have to draw the power flow diagram. If not, it's just sufficient to have this single line schematic here for your reference to assess the performance. Okay, then we go to the question. The data transfer into your circuit, then go to the question. So we have here if resistor adjusted to into 275 ohm. We have here adjustable resistor, you adjust to 275. RF is static or you will fix at 75, but this is adjustable that you have to fix or tuned into 275 ohms. So what happened? So what is the total rotational speed of the motor at no load condition? So A, what you have to find is, so for A, so at R adjustable equal to 275 ohm. So VT no load is how much? You can restate the question here. And so this is the environment or the setting. R adjustable 275. What happened to VT not at no load? And so where start? And so you have already start. And once you have the question, you draw the circuit, key in all the data, produce or derive the equation. So you have the scenario here. So where to start? Start with IF. And so IF right now is how much? So please rewrite the formula, and please rewrite the formula, even though you have right up there, but here is for your mark. If you don't write, you have mistake in typo error or values or unit, so you have marks for your steps lah. Cara kerja tak ada markah, so akan mengurangi markahnya. Because we don't know what you think, we only evaluate on what you write. And so go to VT over RF total. Sorry, RF total. So you can write also another equation, which is RF total is equal to RF plus R adjustable. And also is equal to, we have here, I put the values, 250 volt terminal voltage, because once you draw the diagram, you can see that our field and our armature here are sharing the same voltage of this terminal. So 240 is our terminal voltage for armature, and the same goes to terminal voltage for our field. Mana pergi? Saya terlupa nak klik. Never mind. So look for IF. IF. Any question you can stop me. Ask anytime. RF total. Please perform the exercise together. Don't just listen and you think you understand. Later when it comes to exam hall, all gone. RF plus R adjustable is equal to 240 divided by 75 plus 275 is equal to 240 divided by 350 equal to how much? How much is it? I don't have calculator. Please calculate for me. How much is it?
$0.685.
How much? How much?
0.865.
Okay, 0.865.
No, sorry, 685. 685.
685
Yeah.
ampere. Okay. Okay, then what you have to do is that from this IF that you have calculated, so you look for the how much actually the generated internal voltage. So you refer to the graph here. We have here with IF that we supply, IF that being supplied, how much actually it generates. And you have your graph. So you plot how much actually it generates for this value of IF. And so IF of 0. 0.685 just now, and 0.685, so 0.6, 0.7, so 0.6 is around, this is 0.5, and 0.65, so 0.68 is around here. Okay, so where it goes, so where it dropped to, so almost 200, and goes here, so it can cache, so it goes to almost 200 volts, and 200 volts of EA, and so you can write over there, which is when you refer to the graph, when you refer to the graph, refer to the graph, you can see that EA naught is equal to 200 volt. Oh, what happened? EA naught is equal to 200 volt with the speed and naught is equal to 1800 RPM. Okay, this is your next result of your analysis. Look out for IF, look out for EA naught through the graph. Okay, this is the step. So this is your EA naught. But the next scenario comes with, which is what happened when the motor run at no load, and at 275 ohm, it's produce that kind of a current in the field. That current will produce this kind of flux. The flux value will produce this kind of voltage, and voltage at your 1800 RPM. But when your terminal voltage is at other values, so you have to use this formula, and which is EA over EA naught is equal to NA. So N here you write in small letter because if I write in N this, so the size will not be significant, you cannot see the size. So N in small letter by right. So we have here EA naught, and we have here EA. Wait a minute. We don't have EA yet. So consider the current first, sorry, at no load. At no load, IA is equal to 0. IA equal to 0. So our EA at this moment, see, EA, right again, formula is equal to VT minus IA RA plus RS. Which is EA at no load equal to VT, which we apply at no load also, minus IA at no load. This is equilibrium equation. So you can type India or at the scenario. So when at no load, IA will become 0. And so your EA no load is equal to 240 minus 0 because IA at this time is 0. So your voltage level for the terminal at no load is 240. And first consider the current, then consider how much your EA naught just now. Then we use another equation of EA divided by EA naught is equal to NA divided by N naught. You see, we have calculate what is your EA no load. And EA no load divided by EA naught is equal to N at no load divided by N naught. So you shall have, you include the, put in the calculated data that you have calculated. So EA no load is 240, EA not you 200 equal to N of no load that you want to find divided by reference of 1800 of speed that we measure or we refer. So this is your speed at no load of the shaft. So how much you got? So apa dapat? Speed at no load. Anybody? Boleh nampak ah? Boleh faham ah? Berapa? How much? Guys, you all there? I have to change the data such that the values is what's called can be seen because if you use the original data, you cannot see the difference. So we have to increase the adjustable resistance value so that the intergenerated voltage compared to your terminal voltage can be differentiated. Not you just use almost the same voltage of your terminal dengan EA not tu. So now if we increase the value of R adjustable, so the difference can be distinguished. Kita boleh bezakan secara jelas. So apa dapat value of your speed ni?
Oh, 240 divided by 200 equal to 1.2, doctor.
Yeah, 10 times 1800. How much?
10 times
Times
800.
1800. 240 divided by 200 multiplied by 1800. So that is your speed at no load. How much?
2160.
That one, huh?
Yeah.
Right?
Yeah, right.
So that is your speed at no load. You increase the I adjustable, you get the initial speed at no load, which is higher than 1800 RPM. The other person semua dapat sama, ha? Semua okey kah? Tidak ada orang saja yang participate ni, yang lain mana pergi? Silent. Okay, we just proceed because time we have only a few more minutes. Okay, that's for number 1. The speed at no load condition. Okay, speed at no load. Then assume no armature reaction, means that the current will not be distorted by armature reaction issues. So what are the speed at full load? And what are the speed at full load and what are their speed regulation? Okay, no load we have found. So full load we have to find out. So for B, and let's say we put it here. So B, for B, assume no AR. So V full load is how much? And also your speed relation is how much? So rewrite the question in your own statement that you can understand, so you don't have to cross-check or refer again to the master question. So not the speed, speed, not the voltage, but speed, sorry. So it should be speed at full load and at full load. So your and here and at full load. So again, if no current, we don't have the EA naught yet, so we have to find. But now if we refer to the above question, so means that it's still at this value, are adjustable. And so what are the full load value? So we just start from EA here. Okay, what the speed at full load? So we write the formula, which is EA full load divided by EA naught is equal to N at full load divided by N naught. So EA full load divided by 200 volt of our reference. Sorry. So the first scenario is that at full load, we have to find what is the value of our EA at full load. So at full load, our IL, okay, IL is equal to, you see or not, just now, this scenario, IL is this one, 110 ampere is IL. This 110 is over here. If you can see, should be over here. This is 110 ampere. 110 is here. Mana pergi? 110 is here. And this is IL. IL, not IA. So this is IL. So this IL have to be divided into I armature dan juga I field. So IL here is 110. IL 110. So what? IL is equal to IA plus IF. So IA that we want to find is equal to IL minus IF, which is equal to 110 minus IF that we have calculated just now is 0.685 ampere. 0.685 ampere, which is IA is actually how much remain?
109.315.
315 ampere only. So this is remaining I armature. And so this is your remaining I armature. Okay. So that's I equal of 1 315. So our EA at this 315, 109 at this load. Or we can put at EA full load, and load is equal to VT full load minus IA times RA plus RS. Which is equal to VT at full load, also the same. It's still connected to 240 volts of terminal voltage, but IA is now 109.315. And your RS and RA is 0.02 dengan 0.19. So it becomes how much? 240 minus how much this part?
27.44385.
Berapa?
Yeah. That's a bit.
Wrong. Just put into industry or to the number function. So much 240 minus that number.
212.55 or 56.
Right. Okay. So that's your EA full load. Then use another equation of your EA naught tu. So EA full load over EA naught is equal to N at full load over N naught, which is 212.56 divided by 200 volts equal to N at full load divided by 1800 PM. So your N at full load is how much?
$1913.04.
So you see, when no load, we have 216 something. We put a load, it reduced to 19. So what is our speed regulation? So SR equal to speed at no load minus speed at full load divide by speed at full load times 100%. Okay. So it becomes 1913.04 minus 2160 minus 1913.04 divided by 1913.04 and all together times 100%. You shall get how much of your regulation. Anybody else? Orang je dia respond ni. How much the regulation? Come on, come on. Anybody punching the calculator? Boleh faham kan?
$1.29.
1.29.
Yeah.
1.29. Okay, 1.29. So very stable seems. So for question in the tutorial 8.3 we skip, we just directly go to number 4. So this one also stick with 275 just now. Okay, stick with 275 here, the value. So but we have armature reaction, see, of 1000 ampere turn. So actually what happened to the speed? And compare back to your calculated values here. So for C with armature reaction, see, first you assume no armature reaction. Now we assume we have armature reaction. So what happened? In theoretically, what happened with AR? With AR now, what happened? With AR, we can see that our field current, IF, is normal total of IF we calculate. We have to minus the armature reaction issues. We have EF, we have AR. Okay, right? Divide by number of turn of our field. Just now we calculate our field current of 0.685. And so 0.685. Just now we calculate. And so due to armature reaction, we have armature reaction of 1000 ampere turns. We have here 1000 ampere turns. So minus 1000 ampere turn divide by how many turns of this field windings? 2700. Okay, 2700 turn. So how much it become? Equal to 0.685 minus how much? One divided by 2.7. Much, guys?
Yes, sir. 1000 divided by 2700 equal to 0.37.
0.27. Okay, total it become 0.315. Kan?
0.315, right?
So you see, the amount of field current already changed. So what happened when the amount of field current already changed? So we have to probe again what are the effective internal generated voltage at this new current values. So we have to probe again, and so we have to probe the new value. So 0.315. So where it belongs to? We have here 0.3, 0.4, 0.35 is here. So 0.315 should be around here. Okay. So it should goes up to this value or around here. So this is 100, 150, around 170 or 80 like that. Okay. Let's say we take at 180. So if we take 180, so refer to the graph, we shall get EA naught of 180 volts with our speed of 1800 RPM. Okay, you refer to the graph. So this is our result. It means that when you refer to the graph and your new current value will probe into new EA naught value. Okay. So we find our graph EA naught. So we look at what happened at no load. See what happened at no load, what happened at in terms of their generated voltage, what happened to the speed at no load. And so we consider the no load condition. After we find the EA naught, we put in here the no load conditions scenario. So at no load, IA is equal to 0. And IA equal to 0. So our EA no load equal to VT no load minus IA at no load times RA plus RS, which is equal to 240 volt minus 0, which is equal to 240 volt. So the end result, please put the unit. And then the equation of EA no load divided by EA naught the new EA naught that you have calculated equal to speed at no load divided by initial speed of N naught. So it become 240 divided by 180. Then you calculate. You have put from the graph equal to N no load divided by 1800 RPM. So you shall get your N no load of much
2,400, sir.
2400 RPM. So this is the event at no load condition. Okay. So reconsider at full load. At full load of IL equal to 1100 ampere. So write again, IL is equal to IA plus IF. So IA is equal to I load minus IF, which is 1010 minus how much I F right now, 0.315. So it remains as how much?
$109.685.
So this is our current. So we just continue with the scenario of at full load. Or at IA equal to 109.685. So how much is our EA full load? So it depends on you, you want to write the formula or not, but this will be much help if you suddenly make a typo error or mistake. You will still retain your marks for calculation steps. And much anybody?
Two 216.966.
216, huh?
Yeah, doctor, this is the final answer. Recruit
Hmm.
240.
Okay, see, you reduce to 216.96 or 97. So how much the speed? And so the speed we can see no load is here. Speed at full load will become oh sorry, divided by n not. How much your full load?
2169.66.
So how much your speed regulation compared to without with armature reaction dengan without armature reaction? How much speed? How much totally got? Berapa dapat? Just give me the number. So bear in mind when you perform your calculation or your task during the exam, one question, please try to finish up within 40 minutes, 5 minutes for you all to come back and cross-check. And if you take too much time, so it might drag your time to answer the other question. How much already this values? SR berapa? Means that if you need to compare, other than you have to calculate, so we have to discuss. But right, a brief discuss. You have to compare how much in terms of the initial speed, the speed after full load, and in terms of their response or the speed regulation, and in terms of their reduction percentage of the speed. Is it better or worse compared to the previous scenario? Okay. One is theory, good or bad. Another one is fact. How much actually in terms of their figure and the values of the reduction percentage or unit. Okay, you have to mention all of that. Calculation is one part, but to re-explain the calculation, so you have to put in paragraph, a brief discussion. Right? How much? Sorry? All of you still available? Hai, missing semua dah kah? Mau dah check out lah. How much?
I got 13.41, doctor.
So big difference. 13.41.
Yeah.
10. So might be this one is right. This one is something happen. So you have here 24002169. Okay, doesn't matter. Cross check again because I don't have data right now. So actually, it should be when we have in term of adjustment during our operation. You see here at lower IF compared to higher IF, and we have IF now 0.315. Previously is 0.618. Okay, lower, higher. Higher IF, your speed regulation should be better compared to lower IF. But the smaller the value would be, should be the better it is. Means that your reduction in terms of speed, should be lower. And however, at lower IF, your initial speed is higher. This initial speed, see not, 2,400, 1,900 initial speed. Is that if you compare, this part would be higher in terms of their starting speed. But when you put load, it will reduce to 2169. So if you put, you make a graph, it can become this. The first is lower, but the graph will be quite stable. And it will be quite stable, means that it will not drop so much. And exaggerate, quite stable the speed. Speed regulation will be better, but lower current speed regulation will be worse. So that's if you compare in terms of your speed regulation. Okay, that's all for today. Sorry for the delay and the time that overlaps too much. Okay,